Hi, everyone. Welcome back. We're going to pick up the discussion on traffic queues and queuing theory, because the idea is that level of service based on density is a good performance measure when you're talking about just the uninterrupted flow where the demand doesn't exceed capacity and you want to just categorize the flow of level of service A through F. F is the basically where you have the failure. But in a lot of other places, even on uninterrupted flow facilities, when there is an incident, when there is lane closures, for example, or the demand is exceeding capacity for a prolonged period of time, traffic queues develop, and then vehicular delay might be a good performance measure for us to look at. And also on the interrupted flow side, on a signalized intersection, for example, where every cycle there is a red light and a queue develops and then a queue dissipates at the outset of the green light, we need to have other measures of traffic performance. And what we are trying to do here is define those traffic measures or performance measures using the traffic or queuing theory. And so queues could form at intersections. Queues could form at intersection and roadway bottlenecks during congested periods, and then they could be a source of considerable delay. The theory that we're going to talk about is not unique to traffic analysis. That could happen at industrial plant, at banks, at any of the tellers, bank tellers, for example, or toll plazas, retail stores. We see queue all the time, right, in everyday life. And then some of the concepts that we do here, that we learn here, are applicable to those queues as well. In fact, some of those concepts are derived from those other disciplines. And the purpose of studying traffic queuing is to provide a mean to estimate the measures of highway performance, including vehicular delay. So in queuing theory, we are looking at sort of three things that we are primarily interested in. One is the arrival pattern. How is the arrivals handled? And then the second one is the departures. How are the departures coming about? And then the queue discipline. So arrival patterns, whether they are uniform and deterministic, or if they are exponentially distributed via some kind of a statistical distribution. So if they're randomly distributed, is there a statistical distribution that defines that randomness? And sometimes Poisson distribution could be more appropriate. So for the purposes of this class, we're going to focus on uniform or deterministic arrivals. So that means we are going to assume that if there is 3,600 vehicles per hour coming in, we can sort of translate that into 60 vehicles per minute or 1 vehicle per second. If there is 7,200 vehicles per hour coming in, we can translate it to 120 vehicles per minute or 2 vehicles per second, right? So we will always be able to do that for the purposes of this class. Now, in real world, the arrivals at a location on a roadway are typically more Poisson's distributed. And we talk about these distributions in our 421 class, CE 421, traffic engineering, or modeling and simulation class, CE 529. And there is some discussion of these in your textbook as well. But again, for the purposes of this class, we're not going to get into that. Then you have the departure characteristics. We have the same sort of assumptions that we can make. We can have deterministic or exponential departures. But again, for the purpose of this class, we're going to stick to deterministic arrivals or departures. And then we have another item to worry about in departure characteristics is how many departure channels you have. Now, typically, if you have lanes that are governed by the same traffic light on a roadway, so for example, if there is green light for through movement and there are 2 lanes that are going through, we typically deal with them as one departure channels because they're governed by the same green light. However, if you think about toll plazas where you could go into different lanes and be discharged from those lanes, either via an attendant or if you just have to slow down for an automatic toll collection or whatever, those are treated as different departure channels. So an example of multiple departure channels in traffic will be toll plaza with multiple entrances that you could have. And then the last thing is the queue discipline, whether it could be first in, first out, or last in, first out. So if you have a warehouse thing where you're storing things, that there could be last in, first out type queue discipline, like the things that you're going to put in last, they're going to come out first. But in traffic queues, we're always going to deal with first in, first out. So what I'm going to do is I'm going to just quickly highlight the type of queue discipline that we're going to have in this class, this first in, first out. and we're always going to have deterministic departures. We're going to have always deterministic uniform and deterministic arrival. And then the problems that we are going to solve typically will have one departure channel. So, typically we'll have one departure channel. Okay? So that's something that you have to think about in the context of this course, but obviously you have to be aware of, that there are other types of discipline. Now, one thing is that, we typically represent this with something like this. So for example, we represent deterministic cues with the letter D. And then if there is an exponential distributed cue, we represent that with letter M. So anything that's deterministic or uniform, we represent that with letter D. If it's exponentially distributed, some sort of random distribution, whether it's Poisson or some other one, we represent that with an M. So maybe probabilistic arrivals, we'll just say M. And if it's probabilistic departures, we'll also represent it with an M. So we can actually describe any Q as DD1. So these are the type of Q we are going to deal with. So when I say D/D/1, the first D represents what type of arrival patterns I'm talking about, okay? So this is about arrival patterns. The first D represents that. The second D also represents the departure patterns. And then this third number here represents number of departure channels. So for example, for the purposes of this class, even I want you to be aware of what type of Q and what type of departure channels this MD3 represents. That represents that, you have random arrivals, you have deterministic departures, and you have 3 departure channels. To kind of think about this, like if you have M/2, that represents, again, probabilistic arrivals, probabilistic departures, and 2 departure channels. So for the purpose of this class, all the problems that are going to be dealing with are going to be of this type. All the problems you're going to be dealing with are going to be DD1 queuing regime, but you should still be aware of the fact that what type of queues and arrival patterns and departure pattern does MD3 represent? What type of queue patterns does MM2 represent? Even though all the problems you solve are going to be of this type DD1 queuing regime, okay? So I talked about this already. Arrival rate assumption, deterministic rate, and number of departure channels. So these are what defines a queue regime. And as I said, you should always be able to tell me what, if I give you an MD2 or DD3 or DM2, you should be able to tell me, because the first letter will always represent arrival rate assumption. The second letter will always represent departure rate assumption. And then our number of departure channel will be a third letter. And if it's M, then it's exponential or random distribution, probabilistic distribution. If it's D, that means the deterministic or uniform distribution. Okay. Now, the best way to kind of learn about DD1 queuing regime is through an example. But here, the real world queues, as I mentioned, are typically Poisson's distributed arrivals and Poisson distributed departures. But learning about DD1 queuing regime is still helpful, because a lot of time when we're dealing with intersection delay, for example, we do a lot of our delay calculations using the DD1 queuing regime as assumptions, because those are relatively straightforward. And then we tack on, if we know that our arrivals are Poisson distribution, which we know that they are, we just tack on a penalty of sort of, because we're not going to have these perfect arrivals. Let's say if we have 3,600 vehicles per hour coming in, we know not every minute there are going to be 60 vehicles arriving. Some minutes there might be 70 vehicles arriving. Some could only have 40 vehicles arriving. So there is going to be some discrepancy from minute to minute. So what we do sometimes is that we'll do our intersection delay calculations all based on our DD1 queuing regime, and just sort of tack on a penalty for the minutes where more vehicles might be arriving, and then to give rise to more delay. And so that's why it's important to learn about DD1 queuing regime, and we're going to do that through 2 different examples. Okay, so this is my first example. So let's take a minute and pause it and sort of learn about this. I hope you had a chance to read through the example. I have a national park where 8 a.m. the vehicles begin to arrive at this rate, 480 vehicles per hour. Okay. And the flow declines to 120 vehicles per hour after 20 minutes. And then if the time required to distribute the brochure that ranger gives the entering people, it takes 15 minutes or 15 seconds rather to give one person a brochure, then you need to figure out whether a queue will form and how long is the maximum queue, what's the maximum delay, when will the queue dissipate. Now, the question is, why does queue form? So think about what is a queue. Queue is nothing but, so if you want to define what a queue is, it's always number of arrivals, so total number of arrivals minus number of departures, right? And then, so if we can define the total number of arrivals and total number of departures, we know what the queue length is going to be. So anytime our arrivals exceed number of departures for any given time, then we'll have a queue forming. So now let's think about this. So if we need to, and then we need to be able to write these expressions for number of arrivals and number of departures as a function of time, okay? And in these types of problems, you could use the time unit to be hours. You could choose them to be seconds. So it's completely up to you. But what I found is that, and the problems in this class that we're going to deal with, it is more convenient to define time in number of seconds, okay? So define unit of time to be minutes. So as long as we define the number of units to be time to be minutes, that's going to make our life more convenient in these types of problems. So if we're going to do that, if we're going to define times as per number of minutes, so what we want to do is anytime we see a rate, like for example, in this problem, I see 480 vehicles per hour coming in, and then after 20 minutes, only 120 vehicles per hour coming in, and then it takes 15 minutes to give a brochure. And all these times are in different units. One is in hours, the rates are given in per hour rate basis, and then it takes 15 minutes to give out a brochure. It'll be helpful for us to convert these things, these vehicles per hour rate, into vehicles per minute rate, so that we can define our time in minutes. And then we can write the expressions for number of arrivals and for number of departures as a, as a function of time t that's measured in minutes. So let's go ahead and do that. So first, let's write down the arrival rate. Now, arrival rate in this problem is changing, right? It used to be 480 vehicles per hour from 8 o'clock to 8:20. And then at 8:20, after 20 minutes, it reduces to 120 vehicles per hour. So here is where the DD1 assumption is critical, going from per hour to per minute. Okay, I can make the assumption that because my arrival rate is 480 vehicles per hour, and because I've made this assumption of DD1 queuing regime, because I've made this assumption of DD1 queuing regime, that means I have deterministic arrival, deterministic departure, and one departure channel. That means I can directly convert this 480 vehicles per hour into 480 divided by 60, that's 8 vehicles per minute. Okay, so that's very important. I could say that my arrival rate is 8 vehicles per minute when for t being more than 0. So let's see, 8 o'clock is t equal to 0 minutes. So for t less than or equal to 20, going from 0 to less than or equal to, I have arrival rate to be 8 vehicles per minute. And then what happens to my arrival rate? It reduces to 120 vehicles per hour. But because I'm making a deterministic or uniform arrival pattern assumption, I can translate that into 2 vehicles per minute for t greater than 20. Okay. And I can now do the same thing with my departure rate. I can figure out my departure rate now. Now, the question is, departure rate is based on at what rate vehicles are able to leave the gate of that national park. Now, it takes 15 seconds for the ranger to give you the brochure and maybe greet you or whatever. So that means, could I write down the departure rate in terms of per minute? So if it takes me 15 minutes to give out the brochure, how many vehicles per minute are able to depart the gate? Okay? You can probably figure that out. It's going to be 4 vehicles per minute. It's going to be 4 vehicles per minute. And that rate, it looks like, does not change in given time. So basically, this is a DD1 queuing regime problem where my remains constant, right? My departure rate is always constant. Now, so first question is whether a queue will form. I can see that my vehicles are arriving at 8 vehicles per minute at the beginning, but they can only depart at 4 vehicles per minute. So that means there will be a queue. And I can figure out the size of that queue as a function of time first by doing Q, as I told you, right? Q is nothing but, so my queue length, if I want to write queue length as a function of time, it's just nothing but number of arrivals, vehicles that have arrived, minus number of departures. That's all I need to worry about, right? Number of arrivals minus number of departures. So I need to do, and then when does my queue dissipate? When my queue length becomes 0, that means my number of arrivals become equal to the number of departures total. So again, this is not at any given point of time. I'm talking total number of arrivals minus total number of departures. That's another important to note. So what I need to do then is being able to write the expressions for total number of arrivals, right? So maybe I should have it a different color. So I need to be able to write this total number of arrivals minus total number of departures. So let's write number of arrivals here using the rate. This is the most tricky part here, is that if I'm talking about number of arrivals and as a function of time, so I want to say as a function of time, how do I do that? So the way I do that is that I say, okay, if my time is being measured at t in minutes, the number of vehicles arriving will be 8 times t. Okay, my number of vehicles arriving would be 8 times t. And then I would have, and then I can do the same thing, but this rate will be enforced or will be in place for, or this number of arrival expression will be correct for when I have t less than or equal to 20. Okay. My question to you is, what happens? I want you to give the video a pause and think about what happens when t is greater than 20. What happens to my arrival rate? Does it simply become 2 times t? Think about that for a second. Is that the correct expression? I hope you had a chance to pause the video and think about this. This is not the correct expression because what I'm trying to write is total number of arrivals as a function of time. Okay, I'm trying to write total number of arrivals as a function of time. At t equal to 21, I wouldn't just have 142 vehicles arriving, right? If I plug in 21 here, I wouldn't have 42 vehicles arriving. In fact, what I need to do is, if I'm looking for total number of arrivals, I have to add up all the vehicles that arrived within first 20 minutes. So I'm going to have to say 160 vehicles would have arrived in the first 20 minutes. And then I add to that 2 times t, which is my new rate. Now let's see if that expression is right. So pause the video and tell me if this expression is correct for the total number of arrivals at a given time frame. Okay. I hope you had a chance to pause the video and reflect on it and maybe figure out that this expression is still not correct, because if I plug in t equal to 21, I will have 160 plus 2 times 21 will be 42. So I would have had 202 vehicles arrive at t equal to 21. That's not correct either, because what's the problem here is, the problem is my reduced arrival rate of 2 vehicles per minute has been enforced starting at t equal to 20. So to get the correct number of total arrivals, I need to say 2 times t minus 20 to reflect that this new arrival rate has only been enforced after t equal to 20. Now, if you think about it, at t equal to 21, I would have had how many vehicles arrive? So 160 vehicles arrive in the first 20 minutes. And in the 21st minute, there will be two more arriving. There will be two more arriving. So that means I would have 160 plus 2 vehicle will be there at t equal to 21 minutes. So that's why this expression is the one that's correct, because it accounts for the fact that your t equal to 2 vehicles per minute rate has been enforced only after t equal to 20. So this is the right expression. The good news for us in this problem is that my number of departure equation, my number of departure equation is fairly easy to get because it does not change. So if I want to write total number of departures, that would always be 4 times t, regardless of the value. Regardless of the value. Now that I have total number of arrivals and total number of departures, I can easily write the expression for queue length. Expression for queue length here. It's always going to be total number of arrivals. In fact, I wrote it down, right? So if you look here, I have my queue length expression at the very beginning of this problem, total number of arrivals minus total number of departures. So I can take this expression and set these numbers to that, so these expressions to this formula. So my queue length would always be eight t minus 4t when, right? And then it will be 160 plus 2 times t minus 20 minus 4t for t greater than 20. Does that make sense? 8t minus 4t would be my queue length at any given time. And then 160 plus 2t minus 20 is my number of arrivals. And subtract from that, this is the number of departures. This is the number of arrivals. Do arrivals minus the departures. And I have my queue length. Now, you can always see that the first expression, the queue is always growing and growing and growing. The queue will never be 0 because it's just 4 times t. So as time increases, the queue length will grow. It's only in the second time period where t is greater than 20 is I have a chance of queue dissipation, because now you can simplify these expression. So you could say, okay, it's going to be, so if I simplify these expression, it will be 4t, 4 times t for t less than 20, less than or equal to 20. And then if I write down 160 plus 160 minus 40, I'm just trying to write down minus 2t. So if you simplify this, you'll end up with 120 minus 2t. So this is what I ended up with when t is greater than 20. So please make sure that you verify these numbers. So I have my queue length expression. So now I'm able to answer a lot of these questions. Okay, I'm trying to answer these questions now because, okay, let's look at this. And we probably need to erase some of these things here. I'm going to erase these. So if I look at this, I can say that at t equal to 20, my queue will be maximum. Okay, because it'll be 4 times 20, that's 80 vehicles and going to be on the queue. That's my maximum queue length, right? Because the queue keeps growing until t equal to 20, and it starts to reduce after that. And then you could see, like, if you plug in 20 on both of these expressions, you're going to get the same queue length, right? And then at t greater than 20, that's when queue starts to reduce. Now, so the queue will form because obviously number of arrivals do exceed number of departures. So the queue will form. How long is the maximum queue? It's 4 times t. It's 4 times q. So my answer to that question is, my maximum queue length is my maximum queue length would be 80 vehicles. And it starts to go down. When would the queue dissipate? Means number of arrivals would have become number of departures. That won't happen in the first 20 minutes, but that could happen at the second, after the 20-minute period. And that will happen when 120 minus 2 times t becomes 0, right? Number of arrivals become equal to number of departures. Or you can set the queue length expression to 0. So that means t equal to 60 minutes is when the queue completely dissipates. Now, what is the maximum delay? But before we get into maximum delay, what I want to do is I want to go to the next slide here where I represent this thing more graphically, okay? This is, my departure rate is constant, so you could see that this curve represents the departure curve. So this curve represents the departure curve right here. And then my arrival curve does change from, so my arrival curve was starting from here, goes up to here, and then starting from here, it goes up to here. And then you could see that these two departure curves, these purple lines that I'm drawing, these are what, you know, what these two expressions were talking about, right? So this 8 times t, this is the equation of this line, and 160 plus 2 times t minus 20 is the expression of this line. So basically you had pretty steep arrivals at the beginning. That's what led to the queue. And then at this point, the queue is just into dissipate. And then you could see this FIFO, because it's first in, first out. So you could see that, you know, if you look at the differences between the curve, vertically, they represent what's the queue length. So if you look at any of these sort of vertical distances on this curve, like for example, if you look at this line, or this line, or this line, they represent what is the queue length. And you could figure out the max queue length occurs at t equal to 20. That's your maximum queue length of 80 vehicles. So if you look at the vertical distance, this is 2080. So remember, the time is on the x-axis. So remember that time is on the x-axis. And then the number of vehicles is on the y-axis. So this is sort of your graphical representation of the queue. And so vertical slices on this, the difference between arrival and departure curves. So this red line is your departure curve. Purple lines are your arrival curves. So if you look at any of these vertical differences between these two curves, they give you the queue length. Now, if you look at the horizontal differences between the curves, so I'm going to draw those out as well. So if you look at these horizontal differences, like this one, for example, or any of these, basically what you're looking at there is the delay, the time difference between the departure time, or sorry, the arrival time, or departure time minus the arrival time. So if you subtract those, so you, for any number of vehicles, you could figure out what the delay that they experience. And the delay is defined as, so anytime you're trying to find the delay, so the definition for delay is departure time minus the arrival time. So you can actually figure out the delay for any given vehicle. Okay, for delay for any given vehicle could be figured out by looking at, so like, let's say if you want to figure out the delay of 100th vehicle to arrive. So 100th vehicle to arrive delay would be right here. So if the delay for 100th vehicle to arrive would be right here. I'll just draw this out right here. Okay, so this will be the delay for the 100th vehicle to arrive. And how am I getting to that? I'm basically going to plug in number of arrivals to be 100, find out the time, number of departure to be 100, find out the time, and then that way I would know the difference. So you could see the number of departure because it's 4 times t. So this will be, if you sort of project this point down, you could say, when do the number of departures become 100? It's because it's 4 times t. That means you figure it out by using so if I want to find out 100th vehicle delay, so it will be 4 times t equal to 100. So just plug in, and then that means t equal to 25. That's my answer for when the vehicle departs. Is the departure time for 100th vehicle. and then you figure out the arrival time for the 100th vehicle. The arrival time for 100th vehicle would be, you have to be a little bit careful though. If you look at the 100th vehicle, you have to figure out when does the 100th vehicle arrive. So you could see that, once first 160 vehicle arrive under the first regime. So that's why this 8 times T vehicle equation would be applicable. Okay, so I will say 8 times T equal to 100, and then the arrival time will be 12.5 minutes. So I can do that. So is arrival time for 100th vehicle. And so the delay for the 100th vehicle would be 25 minus 12.5 equal to 12.5 minutes of delay. But that's just, I picked out 100th vehicle randomly. Now you have to be careful about, so when you look at the maximum delay, you just are looking for when the horizontal difference between the two curves is maximum, and that'll be for the 160th vehicle. So go ahead and derive the delay for the 160th vehicle using the same approach, using this approach like I did for 160th. Okay, so I'm going to go, you can pause the video and figure out what would be the arrival time for the 160th vehicle for the max delay, and the departure time for the 160th vehicle, and you will be able to get the max delay. Okay, so with that, I hope you had a chance to pause the video and you figured out that for the 160th vehicle to arrive, the arrival time for the 160th vehicle would be T equal to 40 minutes. Okay, and what time do they leave? What time do they leave when? I'm sorry, the departure time for the 100th vehicle would be when 4 times T becomes 160. Oh, sorry. The departure time for 100th vehicle would be, or 160th vehicle for the max delay is basically when 160th vehicle is able to leave. The arrival time, so let's figure out the departure time for the 160th vehicle, and you can draw this point down right here. I hope you all figured it out. It's 40 minutes when they leave. And when do they arrive? They arrive at T equal to 20 minutes because we know that. So they arrive at 20 minutes. So the difference between the two times will be this one right here. And that difference is 20 minutes. So my max delay, so that's why my max delay is the delay for 160th vehicle is, if I do the difference, is 20 minutes, and that's my answer. Now, if I want to find out the delay for 200th vehicle, okay, delay for 200th vehicle. Now you have to be a little bit careful because 200th, any vehicle that comes in after 160th vehicle, so 161st vehicle, 162nd vehicle, and so on and so forth, 200th vehicle, you'll have to rely on, so you can, the departure equation is not changing, so you can rely on the same equation to find out the departure time. So the 200th vehicle we know will depart, the 200th vehicle will depart at T equal to 50 minutes, right? The 200th vehicle will depart at that time. However, what time does it arrive? For arrival, make sure that you don't apply this first equation because this 200th vehicle is after 160th vehicle. So you know it's the second equation of arrival that will be in force. So you'll have to figure out the arrival time using this equation right here. Okay, so any vehicle after 160th, you'll apply this equation right here you'll apply this equation right here for finding out its arrival time. So just be careful of that. Now, one interesting thing is that when does the Q dissipate? At T equal to 60 minutes. And that's when both curves will sort of intersect with each other. And then arrival, actually, this is a little bit of a mistake here. I should probably shouldn't be extending this curve anymore beyond this point. And after that point, arrival and departure curves sort of move together. So this becomes sort of my common arrival and departure curve right after this point. I should probably maybe create a thicker line here and say, okay, after T equal to 60, once the Q had dissipated, the arrival and departure curve sort of move together. And this is another important point, is that any vehicles that's after 260th vehicle, or I'm sorry, 240th vehicle. So if you look at this number here, it's 240, right? So if you look at this 240th vehicle, any vehicle that comes above 240th vehicle, they're not going to see any delay. They're just going to go to the gate, pick up their brochure, and be able to get this done. Okay, so this is an example that you should be able to work out. And then, yeah, the one last thing is that, if I want to find total delay, aggregate amount of delay in vehicle minutes that all these vehicles experienced, then that way, what I need to do is I need to figure out what's the total area under this curve right here. Oops. So if I'm looking for the total area, then I need to basically just figure out what is the area under the curve here. So I just need to figure out what's the area of this triangle all over the place. So I need to figure that out. So that gives me my aggregate delay. So I should just say for aggregate delay, like means total for all vehicles combined. So remember, you're finding delays for individual vehicles before, for 100, for 160. But if I want to find the aggregate delay, just area of the shaded triangle. Okay, area of this gray shaded triangle. And then that would be basically just kind of looking at this and then figuring out the base times height for this triangle. Okay, so I'll let you figure this out, how to find the area of this triangle. You should all be able to do that, but that's what we need to do. Okay, so that's great. And let me go ahead and figure out some eraser things here so we can erase some things. So I could just basically just about erase everything here. And then just make sure that you know the units of this. I'm going to leave these calculations here for a second because I want to make some points about this a little bit later. So let's go to the next slide here. Now you could actually have, you could actually have the same kind of thing at highway bottleneck. So this was sort of a national park entrance, the problem that we just solved. But at a highway bottleneck, you could have the same thing where you could have some reduction in capacity. So the capacity is what determines the departure rate. Okay, departure rate is what capacity is dictated. Capacity is what dictates the departure rate. So you could have a decrease in the number of through traffic lanes. You could have reduced shoulder width. You could have traffic signal that basically turns red. So now your capacity is 0. Nobody's leaving. Okay, so your departure rate becomes 0 at that point for a certain time. And then when the light turns green, you move at a saturation, sort of high capacity rate, and then the queue dissipates, and then you basically are moving at a steady state. So there is actually an example of this where is like a recurring congestion on highways where physical reduction is number of lanes. So that will every day. At that point, there might be congestion, but sometimes it's incident provoked. Like you have collision that happens, or you have suddenly one day you have sort of work zone or something like that, and that could be another sort of way of where the capacity could be reduced and queues could develop. And then I have another example of this. And this example is, you need to work on this example exactly the same way. You need to basically say, figure out your arrival rate, figure out your departure rate. But in this example, what's different is this thing. My arrival rate remains constant. So my arrival curve will always be one straight line, and my departure rate will vary based on time. And let's kind of quickly read through the example, and then you could solve it on your own. So you have a capacity of 4,000 vehicles per hour and a constant flow of 2,900 vehicles per hour coming in. Now remember, when the demand does not exceed capacity, then your arrivals basically equal to departures. Because you have 2,900 vehicles per hour coming in, and you'll have 2,900 vehicles per hour departing as well. You cannot depart more vehicles than arrive, right? So that means at 8 a.m. when traffic accident, and I should probably change this term here. Give me 1 second. I don't like the term accident. because again, that gives you, I talked about that in the safety class a lot, is that we always want to call it crash or collision. So that's what I'm going to do here. So I'm going to go ahead and edit this to collision right in front of you. Traffic collision is what closes the freeway to all flow. So that means nobody can depart. And then assume a DD1 queuing regime, and you have vehicles coming in at same 2,900 vehicles per hour. So your departure rate from 8 to 8:12 is basically 0 because the freeway is completely shut down. And at 8:12, maybe the CHP, the California Highway Patrol comes in, they partially open the road, and you still have lower capacity. And that lower capacity could be because fewer lanes are open, or maybe people are still sort of rubbernecking at what happened at that collision and all of that. And your capacity is only 2,000 vehicles per hour. And finally, when the wreckage is removed, that's when freeway is at its full capacity. And remember, the freeway will depart at its full capacity until your queue is dissipated. Once the queue is dissipated, then your arrival rate will become equal to departure rate. So here, the problem is, again, you're assuming a DD1 queuing regime. You determine the total delay. Remember, I talked about total delay. That's your area under the curve. And then the longest queue length, and then time of queue dissipation, and the longest vehicle delay. So I want you to work on this example, but I want to show you the chart, and I want you to derive the equation like we derived in the previous example. So again, these are all discussion from the previous example, but I want you to do those. But here I'm showing you, so remember, this is the arrival curve. So this is my arrival curve, which is constant in this problem. But my departure curve start first at 0. So there's no departure at all, right? At t equal to 12, there is some departure. But the problem is the queue is still going, right? The queue is still growing because the arrival is higher than departure because your capacity is only 2,000. So your vehicles are only departing at 2,000. And at t equal to 31 minutes is when full capacity is restored. That's when your departure curves really become steep. And what's the rates of these? So this is going to be 0 rate because nobody's leaving anywhere. This is going to be at 2,000 vehicles per hour. And then this is going to be 4,000 vehicles per hour, this last line over here. So again, as I told you, convert everything into per minute basis and try to work out this example on your own. And then you will get a chance to kind of look at this. Hopefully you'll be able to solve it using like we did in the previous example. Again, these numbers represents the previous example that we solved. But now your arrivals rates are constant, but your departure rate will vary in 2 different ways. So make sure that you're able to solve this problem. Okay. And derive the equation of these 3 lines, but then also of this line as well. Oops. So you're able to hopefully derive the equation of this line as well. And then once the queue dissipates, arrival and departure rate sort of move together. Okay. So you need to figure all these numbers out on your own using the equations how to build those equations you will have to see. And again, to write down the total number of departure equation will be tricky this time because that's the departure rate that varies. And hopefully, but you could do that using the same type of approach that we did for a number of arrivals in the previous example problem. And there is an example like that in your textbook as well. So make sure you look at that too. Okay. So the next example I want to work on, or not work on, but I just want to show you a quick example of this, the last one. It's this one, which is based on example 3.7 of your textbook, is what happens at a traffic signal, where your C is your cycle length, but then you have a red time when nobody leaves, so departure rate is essentially 0. So what I want you to look at is that, from this part to this part, the departure rate on a traffic, so this is again time on the x-axis, cumulative number of vehicles on the y-axis, and you see when the signal is red, nobody leaves, and then when the signal is green, it moves at its departure at a saturation rate. And then once you catch up with the queue and the queue dissipates, then arrivals and departure move together for a while until the signal turns red again. And then, your signal turns red again, then nobody leaves. So then departure rate becomes here, but vehicles keep arriving. So this signal is basically an example where the departure rate varies between 0 and saturation rate, and then the arrival rate, and then again 0 when the signal turns red. And then this cycle keeps repeating itself. And that's your example 3.7 in your textbook. So I want to review that as well. So please go ahead and review that on your own. If you have any questions, feel free to reach out. With that, I'm going to stop here and complete the discussion on chapter 3. Thank you very much.